Our project is predicting lending club loan status by Eric Su, Hongyu Tian, and Rashad Jain. Loans are important in developing new businesses and personal lines, but the risk for both the investor and loanee are sometimes unclear. The motivation for this project is to predict the loan status based off someone's financial background, among other features, in order to quantify this risk. Ultimately, this project aims to reduce the overhead for both the lending club and the loanee in predicting whether or not their loans will end up good or bad. To do this, we have to do some feature analysis, pre-process the data given certain criteria, train machine learning models with the pre-processed data, and analyze the results.
The dataset we are using is called the Lending Club Loan Data. The original dataset had about 900,000 rows and 74 columns, and our purpose is to predict the loan status. There are multiple levels for loan status: a fully paid, charge-off, late, in grace period, and a few more. The first thing we need to do is handling the missing data. As we can see from the graph, all those white chunks are our missing data. So we decide to drop some features. And by looking into the dataset, we found out that most of the missing data are related to the co-borrowers. Since there's only 511 applications had the co-borrowers, we decide to drop them all and only keep the application tab, which indicates whether the loan is an individual application or a joint application with the co-borrowers. And after that, we still have 53 columns left. As we can see now, the data after we drop those missing values looks way better. Then we check the missing portions for each features. As we can see, the top 5, which had over 20% of the data missing. We drop the first and the fifth columns, since the first one is the texture data, and the fifth one is the next payment day, which is not really related to our topics. And for the second to the fourth one, we replace the missing value with a 0. And for the rest, we replace the missing value with either a min or we drop the missing value. After handling the missing data, we drop some texture data and some unnecessary data like ID, member ID, URL, policy code. As I mentioned earlier, our loan types have multiple levels. We can conclude those levels into two groups: good loans or bad loans. And current, issued, fully paid can go to the good loans. In grace period, default, late, or charge-off can go to the bad loans. And based on the histogram, we notice that the data is heavily imbalanced, but we will address this matter later. And after that, we format all the categorical features, like the income source verified status, and the grade, the term, the home ownership. We set levels for those features. After dropping some features, we still have about 40 columns left. And by looking into the dataset, we can certainly tell that some features are highly correlated. Here, we decide to run a multi-collinearity check. The first method we are using is called the variance inflation factor. The variance inflation factor is a way of qualifying the impact of correlations between one feature and the other features within the model, and is typically used for identifying collinearity. And we can tell the VAF does make sense, since it drops the features like the subgrade and keeps the feature like the grade. To verify this, we decide to run the GLM model. After comparing with the GLM summary output, both the VAF and the GLM keep approximately the same features. This gives us a further confidence in the VAF feature pre-processing method. However, we also try one more variation of these two models. Based on the results from VAF, we perform the GLM model again. The null divariance, which shows how well the response variable is predicted by a model that includes only the intercept. In our model, by including these features, we brought the null divariance down to the value of the residual divariance, which indicates these features are necessary to predict the loan status. After that, we generate Pearson correlation heat maps. And based on the heat maps, we can tell that the value above 0.5, and based on the plot, we can tell the public record and the month since last delinquent and the month since last record are highly correlated. It does make sense here, so we decide to remove the two features that are month since last delinquent and month since last record. And after all those steps, we reduce the original 74 columns to 19 columns for our modeling algorithms.
Now that we have our pre-processed data, we choose an experimentation scheme where we first train simple models for binary classification. Then we implement a stacking model. But we also must tackle data imbalance and identify feature importances somehow. Finally, we analyze the results to attempt to tune our models and pre-processing approaches. We will train 6 individual models, which will also serve as base layers for our stacked models. These models include logistic regression, gradient boost trees, linear support vector classifiers, multi-layer perceptron, decision trees, and random forests. After we stack models. One way to stack models is to use out-of-fold predictions on first layer models to serve as features for our second layer model. To illustrate, we would train logistic regression, GBT, and linear SVC models in an out-of-fold setting similar to k-fold cross-validation. Collect the predictions from these models into another feature matrix and use that feature matrix to train an MLP model for our final prediction. In this experiment, we use 2 different base layer models to see if there's a difference between tree algorithms or a mixture of fundamentally different models. Finally, since our data is heavily imbalanced, there is a high chance that using just our original data will not generalize well in real life. We tried 2 different sampling techniques to mitigate this. Undersampling, the majority, and oversampling, the minority, using a technique known as SMOTE. Undersampling will stay truer to the original data, but at the cost of severely cutting the data size from 800,000 to about 125,000. On the other hand, oversampling will almost double our data size at the cost of assuming SMOTE is an accurate oversampler for our data, since SMOTE uses a type of nearest neighbors to generate new data points. Our models were evaluated on 3 metrics. Test error, which is simply the ratio of mislabeled observations to the total. The F1 score, which is a metric that also considers false positives and false negatives in its calculation. And the area under the curve of the receiving operating characteristic, or the AUC-ROC. Both of our VIF and GLM preprocessed models share the same trends when looking across all the evaluation metrics, so we'll just focus on the VIF for now. Overall, the VIF models performed better than the GLM ones. Looking at our test error on the left, we see that the unbalanced data seems to have the lowest error, while our balanced data, particularly our undersampled one, have the highest test errors. Additionally, we see that there's a general lower test error trend when we look at more advanced tree-based models. This is a trend that persists across all the balancing scenarios as well. When we look to stack our models later, this overall improvement seen in tree-based models gives us the motivation to diversify into different stacked models for further analysis. Solely looking at the test error does not tell us enough about our models, however. This type of evaluation is limited only to the results of our experiment but shares no additional information on the nature of the data/models. Therefore, we also look to the F1 score, which provides a bit more information with regards to precision and recall. The F1 score graph is shown on the right. We see the same general trend that we saw in the test scores, in that tree-based models outperform the other models, and that the imbalanced scenario is the top performer. However, this goes against our hypothesis that balancing data should generalize into a better model for new data. Our last evaluation metric is therefore the area under the curve of the receiver operating characteristic curve, or the AUC-ROC. This metric considers the confusion matrices matrices of our experiment, just like test error and F1 score, but also quantifies a measure of separability between the two classes. This separability and the resultant AUC-ROC score is a more accepted criteria for evaluating classifiers. We can see a dramatic difference in model performance when considering the AUC-ROC in both our pre-processing scenarios. Imbalanced data performs poorly when compared to either of our balanced scenarios, with our oversampled scenario performing the best. Tree-based algorithms once again show the highest score amongst all the scenarios. The observation that our AUC-ROC score is significantly different from what we see in the test error and F1 score for the imbalanced data is consistent with what we expect when comparing the effects of balanced data. When we take our models into the stacked modeling algorithm, we notice that our trends are about the same as with individual models. The tree-based stacked model outperformed the mix-based model, and our oversampled data outperforms our unbalanced data in terms of AUC-ROC score. Now we want to take a look at our feature importance from the tree algorithms and compile them together for a top five list of impactful features across all scenarios. When looking through the feature importance across the individual models, we see that the top 5 features are loan grade, last payment amount, remaining outstanding principal, the number of credit inquiries in the past 6 months, and the total amount of late fees to date. Within the context of loan information, these top features make the most sense. The recoveries feature, which is the post-charge-off gross recovery, is also an impactful feature. Basically, those who have recoveries is implied to have once been a bad loan status, and its importance in the tree model suggests that the loan status is affected by the loan history itself. Again, this makes sense in the context as one can assume that a previous bad loan indicates a future bad loan. To summarize, our best individual model was the gradient boosted tree. Our top stacked model was tree-based models, and our best overall model was our stacked tree-based model with just the VIF pre-processing criteria. In the future, we could process the text data as well, correlate zip codes with the default, work with omitted features and other features that we deem as important, and of course, hyperparameter tuning and model diversity. Additionally, a user interface can be created that mimics LendingClub's loan application, but with our selected features to predict the future loan status of an applicant. This would enable an applicant to understand the likelihood of being up to date with their loan based off their history.